prove or give a counterexample. If U is a non-empty subset of R square, closed under addition and additive inverse, then U is a subspace of R square. What U is not said to satisfy, which would make it a subspace by definition, is being closed under scalar multiplication. So the question here is, if U is non-empty, closed under addition and additive inverse, is it necessarily closed under scalar multiplication? We should either prove this to be true for every such U, or find one specific example U for which it is not true, a counterexample. Let's start with a subset U. Assume that it is non-empty, that it is closed under addition and additive inverse, and see what happens. To make U non-empty, we have to pick a vector in R square as an element of U. Any vector except 0, 0 would work, but for simplicity, use the vector 1, 1. The reason 0, 0 does not work is that it does not produce a counterexample, neither a general proof. Next, use that U is closed under addition. So given any two elements in U, their sum must be in U. Applying this to U1 and U2 equal to 1, 1, it follows that U must contain the vector 2, 2. Repeating this argument, one can show that in fact, U must contain every vector of the form kk for k natural number. Technically, this should be proved using induction. Next, use that U must be closed under additive inverse. So given any element in U, its inverse minus U must be in U. Then it follows that U must contain every vector of the form kk for k integer, except 0. Then, it follows also that 0, 0 belongs to U, because it's the sum of two elements already in U, 1, 1, and minus 1, minus 1. So to recap, from assuming that U contained 1, 1, it follows that necessarily U must contain all vectors of the k for k integer. Notice that further using that U is closed under addition and additive inverse will not add any new vectors to U. In other words, the set U given by all vectors of the form kk with k integer is in fact closed under addition and additive inverse. Now one can ask, is U closed under scalar multiplication? The answer is no, because then it should work for the scalar 1/2 and the vector 1, 1, but it does not. So U is a non-empty subset of R square that is closed under addition and additive inverse, but not under scalar multiplication. This makes U a counterexample to the statement that every U non-empty subset of R square that is closed under addition and additive inverse is then a subspace of R square.